Hey everybody, today I want to talk about how n to the n is much greater than n factorial in the limiting case where n approaches infinity. That's basically what this double inequality means. So another way to phrase this is that limit as n approaches infinity of n to the n over n factorial is equal to infinity. It's an infinite limit. So pretty much n to the n is incomparable to n factorial. N factorial is basically 0 compared to n to the n. So this is what we're trying to show. And you can pretty intuitively see this. You can see how n to the n over n factorial is always going to be greater than 1 for any n that's bigger than 1, right? For any natural number n. So here we can see this is n times dot 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 times n all over 1 times 2 times dot 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 times n minus 1 times n. Okay? And, oh, I really messed that up there. N minus 1, there we go. So then you can see that this n over n, that kind of just cancels out. That just equals 1 basically. But then everything else is going to be bigger than 1. So if we take n, let's say n equals 10, 10 over 9, you have n over 2, so that's going to be 10 over 2, which is 5. This is 10. So every number in this sequence is bigger than 1. And then you're multiplying by 1 at the end. So every number is bigger than 1, so you can see that this is definitely going to be bigger than 1. So definitely bigger than 1. But we want to show that it's actually infinite, because bigger than 1 doesn't really mean much for us. So let's show that it's infinite, but how would we do that? Well, the reason why I'm using n as typically, which is a discrete variable, is because I want to do this in a discrete case. I don't want to do it in a continuous case, because then it's harder to work with. If we do it discretely, then we can really see what's going on. We can use products, and that's the motive of what I'm doing here. I'm going to try to use the pi product notation to help us show this. And if we can show that for any integer n values this is going to be true, then we can pretty easily I don't know how easy, but we can kind of intuitively generalize that to any real numbers. I'm not going to go through that step because I'm honestly not too sure how to go about that. But I think this would be good enough to show. And really it's good enough to show that n goes to infinity, because all we want is for n to go to infinity. So if it's a discrete or continuous variable going to infinity, that difference doesn't really matter. So I think this is sufficient anyway. So first off, I want to write this out. So we have the limit as n approaches infinity. Oh, that's a really infinity of n to the n over n factorial. We can write this limit of the quotient as a quotient of the limits. So we have the limit as n approaches infinity of n to the n over the limit as n approaches infinity of n factorial. Okay, so now we can write these as each of these as a product. So we have the limit as n approaches infinity. Let me write that n a little better. Of the product. So I'm going to write this as I equals 1 to n of what's going to give us n to the n. Well, if we think about it, it seems like if we just put n here, that's going to work. Because I'm saying n to the n just means multiply n amount of times by itself, right? This is the same thing here. This is exactly the same. So if you need some time to think about it, then just think about it. Try to write out the terms of this, or not terms, but like all the different terms of that product. And then we're going to divide this by the limit as n approaches infinity, again as the product as I goes from 1 to n of just I. Because if we do that, then we have 1 times 2 times 3 times 4, just whatever that index is, it's going to be here all the way up to n. So this is what gives us our setup. So now what we can do is we can work with this. So I'm going to ignore the fact that it's a limit now, because that's really relevant only at the end. What's relevant now is the fact that we want this to be continuously increasing. So we want we want, or monotonically increasing, I mean, we want the sequence to be just increasing for each successive term. So what that means, because if each of them increases, so let's say if we have n equals 2, that's a certain number, it's going to give us a numerical answer if n is finite. And then if n equals 3, that's going to be bigger than that. N equals 4, it's going to be bigger than that. And it's going to keep going. And then we can prove by induction that n equals k plus 1 is going to be bigger than the case for n equals k. And if we can show that, then we can show that this goes to infinity. And that's it. So let's start with the base case. It would be easy to do n equals 1, but I want to show that's pretty easy. You can do that for yourself. That's extremely easy. I'm going to show that n equals 2 works, because that's slightly more interesting. So we have the limit. Actually, we don't need the limit. We're not working with the limit here. So we're going to take the product from I equals 1 to 2 of 2, since n equals 2, divided by product I equals 1 to 2 of just I. So this gives us is just 2 times 2 over 1 times 2, right? You can easily verify that for yourself. This is just equal to 4 over 2 or just 2. So that's cool. And now we can show all we need is the product for I equals 1 to 3 of 3 over the product I equals 1 to 3 of I. Okay, and we just need to show that this is bigger than that, okay? So this is going to be 3 cubed, so 3 times 3 times 3, that's 27, divided by 1 times 2 times 3, and we can just easily cancel these out, and we get 3 times 3, which is 9 over 2, and that's about, or that is 4.5, which is bigger than 2. So that's the base case done. We showed that the case for n equals 3 is bigger than the case for n equals 4. So that's good. Now we just need to do the induction step. This is slightly more difficult, but not really that bad. So this is going to be n equals k plus 1. Actually, so let's see. So we're basically saying that assuming that n equals k is bigger than n equals k minus 1, yeah, so assuming that, then we can show that n equals k plus 1 is going to be bigger than n equals k. So I guess technically this should be n equals k, like that. No, k plus 1. I'm not sure actually. We'll just stick with it. It really doesn't matter. We just, as long as we know what we're doing. So if we go from I equals 1 to k of actually we can write this as like an inequality instead of writing them separately. We can write it as an inequality. So I equals 1 to k plus 1 of k plus 1. Right, we're just pattern matching there. Over this from I equals 1 to k plus 1 of I. We want to show that this is bigger than the product from I equals 1 to k, to k of k over the product from I equals 1 to k minus 1, just to k of I. Alright, so we just want to show that this is true, because basically we're assuming that every other one prior is true, because we're starting with this, and we're showing that the next one is going to be true. Okay, so we can actually convert this back into what we had earlier, which is just k plus 1 to the k plus 1 power over k plus 1 factorial. This is a lot easier to work with, right? And this is divided by k to the k, or greater than k to the k divided by k factorial. There we go. Okay, so now this is pretty easy to work with, because we can just say, okay, we can rewrite this using exponential rules. This is going to be k plus 1 to k multiplied by another copy of k plus 1 divided by the k factorial times k plus 1. This is just equal to that. That's just an important property of factorials that you should know. And again, we're trying to show that this is greater than k to the k over k factorial. So what's cool is that these two cancel, and then these two cancel. So now all we have to show is that k plus 1 to the k power, k to the k power, is greater than k to the k. And this is pretty easy to show if you're doing some binomial expansions and all that. So that's it. So we showed that the base case works, the induction step works, and what this means is that, like, we started with this, we showed that, you know, the case for n equals 3 is greater than n equals 2, so that's our stepping stone, or like our starting step, and then the stepping stone is the actual induction step. We're taking, okay, we're assuming this is true, we're going to try the next one, and then if that's true, then the next, and the next, and the next, and then that works. I wrote pretty slanted there, sorry about that. But yeah, so that's basically, that ends our proof. We can write a little box here, because that shows that this statement is true. N factorial, or n to the n, is, I forget the terminology, it's like asymptotically larger than n factorial or something like that. So yeah, I hope you enjoyed. Thank you so much for watching, and I'll see you in the next video. Bye guys.